Good day, everyone. We are Group at Turbotech. Today, we are presenting our sea-produced transportation system. Let's begin. So, for the motor selection was based on worst-case sandy terrain. Accounting for rolling resistance and system losses, the required torque was 341 Newton meters and the power is 1.87 kilowatt. So four 600-watt DC geared motors were selected to provide redundancy and improve traction. So next is shaft design analysis. Our shaft will have 2.5 safety factor and allowable shear of 48 megapascal. So based on calculation, the minimum diameter of shaft is 33.7 millimeter, but our group select 40 millimeter. So this selection provide additional factor against fatigue and dynamic impact loading.
Our design consists of simple but practical concepts. First, the frame of our design has additional beams in the middle to increase its maximum strength to withstand the load of 100 kg. Next, we put the box that stores the battery and electronic components such as the motor, controller, and buzzer at the front of the wagon. This is to ensure the ease of access during maintenance. The battery box also has a detachable lid and ventilation holes to ensure airflow to cool down the components that prevents overheating. Our wagon also consists of four independent tires and each of them are connected to a motor through their gears with a chain. This is to give them more power to move and carry the load while having better maneuverability. The storage box floor consists of three layers: a plate, a damping pad made of polyethylene, and the actual floor. A load cell is present with the same level with the damping pad. When the sea product is loaded into the storage box, the damping pad will hold the plate above it to prevent tilting and give the load cell a proper reading. When the load cell detected the load exceeding 400 kg, it will activate a buzzer as a warning to reduce the load to a safer weight. For a simulation, we simulate the effects of 400 kg load on the frame of the wagon. As shown in the simulation, the support beam helps the frame in handling the load. The simulation shows that the frame only experiences minor stress and strain while having non-significant displacement.
For thermodynamics, the electronics housing is chosen for the calculation of each component in the housing, found to be that it totals up to 89.37 watts. Initially, for the advanced design, it is found to be that the temperature results in 46 degrees Celsius. Although it is below the 50 degrees Celsius of battery threshold, it still can be added with more ventilation. Therefore, after ventilation is added, the final temperature of the housing is 40.66 degrees Celsius. For fluid, the main goal is to make sure that the wagon does not topple when it operates and it is exposed to a windy environment, in this case, a sandy beach environment. For the calculation part, the side part of the wagon is chosen and it is calculated that the maximum wind speed of 195.56 kilometers per hour of wind will cause the wagon to topple. And for the simulation part, which is done using ANSYS Fluent, it is found that the frontal impact, the red zones show maximum air resistance, stagnation at 196 kilometers per hour, and it is significantly increasing the drag.
For the mechatronics of our product, it includes a server, which is the joystick, and a receiver, which is the wagon itself, and it works by wirelessly transmitting data from the joystick to the wagon. For the controller, it will be powered by 18650 lithium ion cells, and for the input, It will be done by JHD400XR4, which inputs the movement, and it will be processed by ESP32 DevKit V1 microcontroller. The data is then transmitted via NRF24L01. The data transmitted by the controller is then received by another NRF24L01, which acts as the input for the receiver. Data is then processed by another ESP32 DevKit V1 and is sent to a motor controller where movement is commanded to the DC motor. Other than that, during overloading, a red LED and buzzer is implemented and it will light up and buzz. For manufacturing, we chose batch production as our production strategy, and it is utilized to balance medium production volume with product variation, in which the key benefits are efficiency, it minimizes production time and material wastage compared to one-off manufacturing, and quality control, which prioritizes proper handling of each operation before proceeding to the next stage, and finally, cost management, which reduces downtime and excessive changeover costs typically found in mass production process. It will include four critical steps. The first one is fabrication. Galvanized steel is CNC cut and joined via arc welding to form a durable chassis. Next is mechanical assembly. Custom shafts are turned on a lathe mounted on bearings and chain driven by electric motors. The third one is electronics, in which Arduino controllers and load sensors are secured using non-corrosive silicone sealant to prevent vibration damage. And finally, finishing, where parts undergo grinding and polishing for safety, followed by high-temperature lubrication to reduce wear.
I will now cover the material selection and economic analysis for our wagon. For our material strategy, we prioritize balancing industrial durability with production for the main chassis. It provides the necessary 200 gigapascal structural stiffness to carry our heavy load, while the zinc coating acts as a sacrificial anode to prevent rust in the beach environment. This is significantly more affordable than using full stainless steel for the entire frame. However, for the drive shaft, we could not compromise. We selected the stainless steel 303 since this is a high torque rotating part. Any surface rust would destroy the bearings and cause mechanical failure. This hybrid approach gives us maximum reliability where it counts without inflating the price. In terms of economics, our Turbotech wagon, to make a single wagon unit, it costs 9,736. And for our selling price, we sell it at 25% profit margin with the final cost of 10,953. And the return of investment is 12.5%. For market competitiveness, our Turbotech wagon is electric powered. It is also easy to use and requires one operator. And it is much cheaper compared to our competitors, Longstar Buffalo. Looking at our financial feasibility, the ROI is 12.5%. It is a healthy return. As for net present value, 2.44 million indicates a strong project viability. As for break-even units, we need to produce 106 units, whereas our factory produces 150 units per year.
Risk analysis was conducted to identify mechanical, electrical, and environmental hazards. Potential risks include overload, fatigue failure, electrical overheating, and corrosion due to sand and moisture exposure. These risks were mitigated through the use of safety factor above 2.5 and corrosion-resistant material, ensuring safe and reliable operation. The project supports multiple sustainable development goals. It contributes to SDG 8 by improving labor productivity and safety, SDG 9 through engineering innovation, SDG 12 by optimizing material use and longevity, and SDG 13 by lowering carbon output in manual logistics.